Dear students, in this video on electromagnetic induction, we will do numerical problems based on Faraday's laws of electromagnetic induction and Lenz law. So let us begin with the first numerical. This is a NCERT problem and a board problem also, very often asked. So let us look at the question first. A rectangular loop and a circular loop are moving out of a uniform magnetic field region, as shown in this figure, to a field-free region with a constant velocity v. In which loop do you expect the induced EMF to be constant during the passage out of the field region? The field is normal to the loop. So first let us try to understand the question. According to this rectangular loop and this circular loop, they are moving out of this magnetic field which is normal to the plane of the loop directed inwards, and they are moving out with constant velocity. Now you have to find out which one of them will have constant EMF while passing out or while moving out from this magnetic field. So let us see how we do it. Now the relation for induced EMF is minus d phi by dt, and this phi is magnetic flux, so it is B into A, and you know that here B and A are parallel, so and B is constant, so B can be taken out, then you get minus B dA by dt. Now you see that B is constant. So if dA by dt, that is rate of change of area, if this is constant, then induced EMF will be constant. So for the rectangular loop, the rate of passage, the rate of change of area will be constant, so induced EMF will also be constant. You see, for this rectangular loop, it is moving out with constant velocity v, so the rate at which the area will leave this magnetic field will be constant. So for rectangular loop, this is constant. Now think of this circular loop. If the circular loop is at this stage, look at this smaller area, when it reaches further, a larger area is passing out. So the dA by dt or rate of change of area is not constant for the circular loop. So the induced EMF is not constant. Okay. So the next one is, this again is a board problem and asked very often, an NCERT problem also. So predict the polarity of capacitor in the situation described in this figure. So you have to tell the polarity of this capacitor shown by plates AB. Now here you see, when this south pole is approaching this loop, then according to Lenz law, this loop must behave like a south pole for observer at this point. So that means the loop must develop a clockwise current. So this is going to be clockwise current, right? And if you observe from the left hand side, from here, the north pole is approaching this loop, then according to Lenz law, this side must look like a north pole. North pole means this side, when you observe from this side, it should look like anti-clockwise. Then also the current will be like this only. So in both the cases, the direction of current, induced current, is going to be same, and that will make the plate A as positive, because see, the current will move this way and will deposit positive charge on plate A. So according to this figure, when north pole of left magnet approaches the ring, it behaves like a north pole. Now according to Lenz law, So the current must appear anticlockwise. So the plate A of capacitor must become positive. When south pole of right magnet approaches the ring, it must behave like south pole according to Lenz law. So the current must appear clockwise. So plate A of capacitor must become positive in both the cases. Right? So this again is your NCERT problem and also a board problem. So here, let us try to understand the question. In this figure, the arm PQ of the rectangular conductor is moved from x is equal to 0 outwards. Now the uniform magnetic field is perpendicular to the plane and extends from x is equal to 0 to x is equal to b and is 0 for x is greater than b. So let us look at this diagram first. According to this question, this PQ conductor is moved out and the magnetic field extends from x is equal to 0 to x is equal to b, and beyond it, here the magnetic field is 0. Okay. Now the magnetic field is set up normal to the plane of the paper. So it is parallel to the area vector of this closed loop, right? And let's see what they next say. Only the arm PQ possesses substantial resistance R. Now consider the situation when the arm PQ is pulled outwards from x is equal to 0 to x is equal to 2b. See, this place was b and this place is 2b. So this arm PQ is pulled from here, passing through b up to 2b. And then it is moved back to x is equal to 0. Then it is moved back to x is equal to 0. Right? Obtain expression for the flux, the induced EMF, the force necessary to pull the arm, and the power dissipated as joule heat. Sketch the variation of these quantities with distance. Okay. So let us try to understand the question once again. Here we have this arm PQ as conductor and it has sufficient resistance R, and it is moving on this conductor, but the resistance of this frame is negligible as compared to this PQ arm, right? The magnetic field exists from x is equal to 0 to x is equal to b, and beyond this magnetic field is 0. Now what is happening? This PQ is pulled out from this place x is equal to 0 to x is equal to b, and then it is pulled back from x is equal to 2b to x is equal to 0 at constant velocity v. Now during this passage you have to find out the magnetic flux, relation for magnetic flux, relation for induced EMF, the force required to move the conductor, and the power dissipated. And you have to draw the graphical variations also. So I hope the problem is clear, and let us move to solution now. So here, okay, let us look at the solution so you'll be able to understand the variation. Now see, the magnetic flux phi is equal to vector B dot vector A. This is scalar product of area vector and magnetic field, and this is equal to BA, because see, area vector and magnetic field are parallel in this case. So you know that scalar product is BA cos theta, and when this theta is 0, this becomes 1. So you get BA. Now the area of this rectangular loop is the length L of the PQ and the area, the breadth X. So the area is L into X, and for X between 0 and B, 0 is less than equal to X is less than equal to B, this phi increases linearly. You can see that here, this phi is equal to B L X. So when X is increasing at constant rate, velocity V, then this phi will also increase at constant rate. It is an equation like y is equal to mx, you see, a linear equation where this slope m is equal to bl and this y is equal to phi. So if you look at this graph, you see, this is x and this is the flux phi. So this is increasing linearly till it reaches at B. This point is B. Now after this, what is happening? Look at it. Let's get back to it. Yeah. So from here to here, the flux is increasing linearly like this. But after this, for this part, this flux is 0. For this part, it becomes maximum, that is B L B, and the total flux will be sum of this flux plus this flux, which will be B L B and constant. So from here to here, the flux will remain constant, the sum of these two. And while coming back also, from here till here, the flux will be constant, and from here to here, the flux will reduce linearly. So let us get back to this once again. See. So this is the relation for flux. At x is equal to b, the flux will become BLB, or between b is less than or equal to x is less than equal to 2b, flux will phi is 0. So the total flux will be the sum of two flux between sum of flux in the two separate regions, and that is BLB or constant, right? So you get initially the flux is increasing linearly, then this is B, this is 2B, it becomes constant. So this is outward motion, and in the same graph the inward motion is also shown. So when from 2B to B, the flux is constant, and then B to 0, this flux becomes 0. So on the same graph, two motions are shown. Okay. So here what I have written is, for motion from 2B to 0, reverse happens. Now let us move on to the next part for induced EMF. Now see, for 0 is less than or equal to x is less than or equal to b, the relation for induced EMF is minus d phi by dt, and put the value of phi here. So minus d by dt of BA, and magnetic field is constant, so taken out. So d by dt of Lx, the area is length into breadth. L is also constant, so taken out, and dx by dt is velocity of the conductor. So E is equal to minus BLV. You see, induced EMF is minus BLV, B is constant, L is constant, velocity is constant. So induced EMF is constant but negative, and from B to 2B, the flux phi is equal to BLB constant. So differentiation of a constant is 0. So d phi by dt will be 0. Induced EMF will be 0. So now you can look at the comparative graph here. See, this is x is equal to 0, x is equal to b, x is equal to 2b. So from here to here, the flux is increasing linearly, but EMF is constant minus BLV, negative side. Here, when the flux becomes constant, the induced EMF becomes 0, and beyond it, between 2B and B, while coming inwards, the flux is constant EMF is 0, and between B, x is equal to B to 0. See, x is equal to 0, B, to B, B 0. So, when this flux is decreasing linearly, the induced EMF will be plus BLB, it will become constant. So, these two are graphs for induced EMF and flux. Now, the third one is to find out the force. Okay. See. So, if the induced EMF is 0, the induced current will be 0 for this part. Alright. Now, the force is between 0 and B. The relation for force you have done is minus B square L square V upon R. You have done this relation, and this force is also constant. So, the force is constant, this, and for this part, that is B to B and back to B. For this part, the induced EMF is 0, that means induced current is 0, and you know that force is equal to ILB. So, when I is 0, force is also 0. For this part, the force is 0, and while moving inwards, when this BLB is constant, that is induced EMF is constant and positive, force will also be constant and positive. Now, let us move on to the last part, which is power. Here. For x between 0 and B, the relation for power is B square L square V square upon R. And you see that relation for power is I square R. So, whether the current is negative or positive, power will be positive only and constant, positive and constant. So, even when the induced EMF is negative, force is negative, power is positive. And when induced EMF and force are positive, power is also positive and constant. So, this is a very interesting problem, and it has been asked in board in many times. So, let us move on to the next problem, an unsolved problem from your NCERT book. The question is, a long solenoid with 15 turns per centimeter has a small loop area of 2.0 square centimeter placed inside the solenoid normal to its axis. If the current carried by the solenoid changes steadily from 2 ampere to 4 ampere in 0.1 second, what is the induced EMF in the loop while the current is changing? So, first of all, you should try to understand the problem. Things become easy when you try to draw this diagram. So, here I have taken a solenoid, and the magnetic field inside the solenoid is parallel to its axis. So, this is the magnetic field, and this is a small loop inside it, and what is given is that its axis is, see, loop area is 2.0, very small, and its axis is, it is placed normal to its axis. So, the area of the loop is normal to this magnetic field. Axis is along this direction only. Okay. So, we can say that the area vector and magnetic field, they both are along the same direction. Okay. Now comes the problem. So, we have to find out induced EMF, and the relation for induced EMF is d phi by dt, minus d phi by dt. So, first we have to find out this flux, and see, the things which are given is the number of turns is 15 turns per centimeter, that is 15 turns upon 10 raised to the power minus 2 meter, or 15 into 10 to the power 2 turns per meter. We have to convert the number of turns per unit length in SI unit. Area of loop is 2 square centimeter, that is 2 into 10 to the power minus 4 square meter. And you know that magnetic field inside the core of a solenoid is mu naught Ni. Relation for flux here will be BA, and B and A are parallel as I just showed you. See, this is magnetic field and area vector is also along the same direction. So their scalar product will be B dot A or BA cos 0, which will be B only. Relation for induced EMF is minus d phi by dt, and I can very well write it as minus delta phi upon delta t, and that is final flux phi 2 minus initial flux phi 1, and final flux phi 2 will be AB2 and initial will be AB1. So taking A common, area common, you get A into B2 minus B1 upon delta t, right? And we can put the values here now. Now this induced EMF will be minus area A, and relation for magnetic field is mu naught Ni. So mu naught N constant hai, we can take it out. So mu naught N is outside. Here you get I2 minus I1. From this relation to this relation, right? And now we can put the values here. See, area is 2 into 10 to the power minus 4. Mu naught relative, this is permeability of free space, 4 pi into 10 to the power minus 7. Number of turns per unit length, 15 into 10 to the power 2. And the final current was 4 ampere minus 2 ampere. See, current changes steadily from 2 ampere to 4 ampere. Time given is 0.1 second. So here, so 4 minus 2, final current minus initial current, and the time delta t is 0.1 second. And putting all the values and simplifying, you get induced EMF as 7.5 into 10 raised to the power minus 6 volt. So the next problem, this is also an NCERT unsolved problem and also board problem. So let us try to understand the problem first. Here, a rectangular wire loop of side 8 cm and 2 cm with a small cut is moving out of a region of uniform magnetic field of magnitude 0.3 Tesla directed normal to the loop. What is the EMF developed across the cut if the velocity of loop is 1 cm per second in a direction normal to the longer side or shorter side of the loop? For how long does the induced voltage last in each case? So let us try to understand it this way. We have uniform magnetic field directed normal to plane of paper, and here we have a rectangular loop with a small cut. Sides are given 8 cm and 2 cm, and for the first case, let us look at the first case. What is the EMF developed across the cut if the velocity of loop is 1 cm per second in a direction normal to the longer side? So this loop is dragged out from this magnetic field with velocity v, okay, and the longer side is being dragged out. So let us see what we get. Yeah, see, the relation for induced EMF is BLV. So magnetic field is 0.3 Tesla, it is given to you. the side, this longer side is 8 centimeter, that is 0.08 meter, and the velocity is 1 centimeter per second, that is 0.01 meter per second. So putting all the values, the induced EMF is 24 into 10 raised to the power minus 4 volt. This is the induced EMF. And now what if it is dragged out from the smaller one? If it is dragged out by this smaller side, so now the length is going to be this one. See, when it is dragged from this side, there will be no induced EMF in this one and in this one, because here the velocity and length are parallel. For this relation, BLV, magnetic field, length and velocity, all three have to be mutually perpendicular. So when you're moving like this, the velocity and the length are parallel. Magnetic field is perpendicular. But for this conductor, the velocity, length and magnetic field, all three are perpendicular. So induced EMF is BLV. B is 0.3 Tesla. Length is 2 centimeter, that is 0.02 meter. Velocity is same, 0.01 meter per second. And you get 6 into 10 raised to the power minus 5 volt. Now, the second part is, for how long does the induced voltage last in each case? See, the induced voltage or induced EMF will last till there is change in magnetic flux. Means till this whole thing is out of the magnetic field. So velocity is known and it has to cover this much of length with velocity 1 centimeter per second. So the time taken will be, so the induced EMF will last till the loop moves out of magnetic field. So for case A, the time taken will be equal to length. This is the length 2 centimeter. 2 into 10 to the power minus 2 upon velocity 1 into 10 to the power minus 2, that is 2 seconds. In this case, you have longer length to pass through it. It is 8 centimeter. So 8 centimeter upon 1 centimeter per second, that is 8 seconds. So a very interesting problem. See, the next problem is based on this only. Suppose the loop in exercise 6.4, which was the previous one. Suppose the loop is stationary, but the current feeding the electromagnet that produces the magnetic field is gradually reduced so that the field decreases from the initial value of 0.3 Tesla at the rate of 0.02 Tesla per second. And the cut is joined and it has resistance of 1.6 ohm. See, now the situation is different here. Okay. Here what is given is the magnetic field as such is changing and the conductor is totally closed. It is not changing its position. It is stationary. Magnetic field is being changed here, right? And the resistance of this loop is given. Now the induced EMF is minus d phi by dt, that is minus d, and phi is b into a, dba by dt. And here area is constant but magnetic field is changing. In the previous case, magnetic field was constant, area was changing. So area is outside, minus d a dB by dt, and induced EMF now is going to be, the area is length into breadth. Length is 8 centimeter, 8 into 10 to the power minus 2 meter. Breadth 2 centimeter, 2 into 10 to the power minus 2 meter. And the rate of change of magnetic field is given to you. See, 0.02 Tesla per second. So you multiply by 0.02 and multiplying you get 3.2 into 10 to the power minus 5 volt. Okay. So the first part. Now, how much power is dissipated by the loop as a heat? And what is the source of this power? Okay, this is not asked, but we need it. Now, induced current, because to find out power, we need to find out current. So, induced current will be induced EMF upon R, and it is given to be 1.6 ohm. R is 1.6 ohm. So, you get 2 into 10 to the power minus 5 ampere. So, induced current is this much, and then the power dissipated is I square R. So, the value of I is given here, 4 into 10 to the power minus 10, and R is 1.6. You get 6.4 into 10 to the power minus 10 watt. Remember, it is power. Now, this power is provided by the external source, which is changing the magnetic field. See here, the loop is stationary. It is not being pulled, no, it is not being dragged, but we are changing the magnetic field, and some energy is being used in changing the magnetic field. So it is the external source. It is the external source which is spending that power. Okay. So this again is your NCERT problem only, unsolved problem. A 1.0 meter long metallic rod is rotated with an angular frequency of 400 radian per second about an axis normal to the rod passing through its one end. The other end of the rod is in contact with a circular metallic ring. A constant and uniform magnetic field of 0.5 Tesla parallel to the axis exists everywhere. Calculate the EMF developed between the center and the ring. You have done a similar derivation here. So according to this question, we have a rod of length L. Its center is fixed and a magnetic field exists normal to this plane of this ring, and this end is rotated on this metallic ring with angular frequency omega. Now, the relation for induced EMF is, see, L is 1 meter, omega is 400 radian per second, B is 0.5 Tesla. So, induced EMF is given by this relation, half B L square omega. Put all the values, see, multiply, you get 100 volt. So, I want to add one more thing. Supposing we had many similar rods like this. Say, let us assume that we have, these are spokes of a cycle. Many similar rods, you know, they can be spokes of a cycle. Then across each spoke, the same 100 volt will be developed. And they all are connected in parallel. So, in that case also, the induced EMF will be 100 volt only. Such variations of questions are also asked. Another NCERT problem, unsolved problem. Here, a horizontal straight wire 10 meter long extending from east to west, falling with a speed of 5 meter per second at right angle to the horizontal component of Earth's magnetic field, 0.3 into 10 raised to the power minus 4 Weber per meter square. Now, first part, what is the instantaneous value of EMF induced? So, let us try to look at the situation. You know that Earth's magnetic field extends, horizontal component of Earth's magnetic field extends from, extends along north-south direction. So, I have shown north-south direction like this, and this is horizontal component of Earth's magnetic field directed towards the north. and the wire is extending east to west. So wire is along east to west, and see the directions are in horizontal direction, horizontal axis, horizontal plane. Okay, now this wire is falling vertically downwards here. So you know that the angle between east west and north south will be 90 degree. That is angle between L and B is 90 degree, and it is falling vertically downwards. So angle between magnetic field and velocity is 90 degree. Angle between length and velocity is also 90 degree. So B, L, V, all three are mutually perpendicular, and the induced, see, L is 10 meter, velocity is this much, horizontal component of Earth's magnetic field is 0.3 into 10 raised to the power minus 4 Weber per meter square, and induced EMF is BLV, and here the value of magnetic field is horizontal component of Earth's magnetic field. So putting all the values and simplifying, you get 1.5 into 10 raised to the power minus 3 volt. So the first part of question was, what is the instantaneous value of EMF induced in the wire? Second is, what is the direction of EMF? You have to find out direction of EMF. Now to find the direction of EMF, you have to use Fleming's right hand rule. So when you apply Fleming's right hand rule, what you do is extend your thumb, index finger and middle finger of right hand. Remember, it is right hand, mutually perpendicular to each other. Your index finger is along BH. Your velocity is shown by your thumb, right? And then the current will be, induced current will be shown by your middle finger. So if you do that way, the induced current will be from west to east, right? And if you do so, applying Fleming's right hand rule, the induced current is directed from west to east. So eastern end, this eastern end will become positive and the western end will become negative. And the third part is, which end of the wire is at higher electrical potential. So naturally this end becomes positive, so eastern end is at higher potential. So again, NCERT problem as well as board problem. A jet plane is traveling towards west at a speed of 1800 km per hour. What is the voltage difference developed between the ends of the wings having a span of 25 meter, and if the Earth's magnetic field at the location is 5 into 10 raised to the power minus 4 Tesla and the dip angle is 30 degree. So here I have shown you directions east to west like this, and the plane is flying. You see, the jet plane is traveling from towards west. So the plane is traveling towards west, and if the plane is traveling like this way, its wings will be perpendicular to it. So that means along north south. So look at it. The velocity is towards west. The wings are given wingspan of 25 meter and along north south. And see here, while traveling, this plane will be cutting the vertical component of magnetic field. So while moving, this wingspan, you can treat it like a rod, and it will be cutting the magnetic field, vertical component of Earth's magnetic field. it will not cut horizontal component. See, horizontal component will be along this direction. So this rod will not cut horizontal component. It will cut only the vertical component at right angle. So here again, you see, velocity, length and BV, they are perpendicular and the EMF will be induced according to this relation. So let's see what are given. L is 25 meter, velocity is 1800 km per hour, magnetic field is 5 into 10 to the power minus 4 Tesla and dip angle is 30 degree. So here the induced EMF will be BV, the vertical component of Earth's magnetic field, BV LV, and the vertical component will be B sine delta LV, and then put the value of B, and sine 30 is 1 by 2 and L is 25 meter and velocity is 1800 kilometer, multiply by 5 upon 18, it will become in meter per second. This becomes in meter per second. So it is 500 meter per second. Simplify, you get 3.125 volt. So this is a board problem. You get many similar problems in your board exam. So with this, I come to the end of this video. I hope it is beneficial to all of you. Thank you very much for watching.